This next theorem doesn't have the name. We're just going to call it Theorem 0.023. And it's you could call it a lemma, and we're going to use it as one. I just don't like that phrase. I don't like saying, hey, this is only good for proving another theorem. Although that would be a correct name, I'm just going to avoid that. So we'll say given, and this is a theorem, so it's not going to have a proof. We'll do the proof in just a minute. So given triangle ABC, we'll say let there be a point M, and we'll say let M be the midpoint. So midpoint of segment BC. Let's draw this out while we're doing it. So just given any old triangle ABC, we'll say we have a point M here, and that will be the midpoint of BC. So we'll say that these two are equal, and I know I didn't draw it well, but we'll go with it anyways. And we'll also say let D be a point such that D forms a line with A and C, but it's on the other side of C, opposite from A. So we'll have a point D out here, and this will be the point C. And we'll say, oh, need a period here. Extend AM to a point E. So AM is here. Let's say we extend it here. Such that AM is congruent to ME. So these two things are going to be of equal length. Then this is the conclusion part of the theorem. E is an element of the interior of angle BCD. Alright, so the proof of this. Actually, let's not go with a proof yet. Let's go with call it pre-proof. So pre-proof. Alright, what do we want to show? We want to show, so want to show 1, E is on the same side of CD as B, and we also want to show E is on the same side of CB as D. And by an earlier definition, that will prove that's in the interior angle of BCD. So let's scroll down a little bit. I'm going to redraw that picture. So we'll just draw the same exact picture right here. Given A, B, C, with a point D out here, C, A, B, M, and we'll put point E out here. The scale that I've drawn that to isn't very accurate, but that's not what we're going for. I think anyone who's watching this playlist can forgive me for that. So we'll say let's scroll down a little bit. Try to fit this all on this page. So, proof. Since AE intersects CB, E must be on the opposite side of CB. Then, from, well, let's see, don't need that there. So, E must be on the opposite side of CB from A. And that's by the Posh separation axiom. Well, that's pretty much the same thing as here, so similarly, since AD intersects CB, oh, that should be a segment there, and this will be the line CB. We also can say D is on the opposite side of CB from A. Finally, E and D are on the same side of CB. Alright, so that is our proof. So we've shown that E is on the same side of CD as B, and E is on the same side of CB as D. So we've proven this earlier statement given right here.